Have you ever noticed that your AI assistant seems to live in a perpetual present? Strip away the technical jargon, whether we call it catastrophic forgetting or context rot, the fundamental diagnosis remains exactly the same. Current AI systems simply cannot accumulate knowledge across time. They operate in a perpetual present. What isn't actively held in their immediate context window effectively does not exist. At the root of this limitation is a structural divide. Large language models operate with two distinct memory modes: the frozen, long-term memory of their trained weights and the ephemeral, short-term memory of their working context. Right now, there is no intelligent bridge between these two states. When an AI agent reaches the limit of its working memory, older information is either truncated or lost entirely. Everything interesting regarding the future of AI development is happening right in that gap. Today, let's explore two very different philosophies attempting to solve this, two roads leading to the exact same destination. The first approach addresses the problem directly from the engineering trenches. It focuses on the immediate physical cost of holding memory in hardware and the failure of basic human-designed rules for compacting information. Instead of relying on human-written prompts to tell the model how to summarize its past, this approach trains the AI to self-summarize its own context intelligently before it gets cut off. Through reinforcement learning and indirect rewards, the model is given tasks that are completely impossible to finish without effective self-summarization. This forces the model to discover what matters and preserve it through trial and error. It's a pragmatic, highly elegant solution, but it remains a just-in-time patch. The preserved memory is just a compressed text summary, better than before but still lossy. It doesn't claim to solve the underlying statelessness of the machine. The model still forgets, it just forgets better. The second approach operates at a completely different altitude, the architectural paradigm layer. Instead of merely patching the context window, it asks us to redesign the entire underlying system. This philosophy proposes creating a hierarchy of nested optimizers that operate at multiple timescales simultaneously. By distributing knowledge across different memory modules, some updating very fast, others updating very slowly, information can theoretically persist and be recovered long after the immediate context window closes. It is a bold vision aimed at actually solving catastrophic forgetting, ensuring that new training doesn't unpredictably erase old knowledge. However, this is highly theoretical. Whether our current AI hardware, which is heavily optimized for standard transformers, can even support such complex multi-timescale infrastructure remains a very open question. Despite their massive differences in scope, both of these approaches share a profound philosophical foundation known in the field as the bitter lesson. They both independently arrive at the exact same conclusion. We must stop imposing human-designed heuristics on our models and instead let the learning process do the work. Whether it is replacing hard-coded prompt rules with a learned summarization strategy, or replacing fixed optimization rules with a self-modifying architecture, the core principle is identical. Neither approach imposes the final answer. Both simply set up the environment and let the training process reveal it. Both share a deep contempt for prompt engineering as a substitute for true learned capability. Yet, looking at both of these advancements, there is a crucial element missing. Both frameworks vastly understate the data problem. If we want AI agents to be truly continual systems that learn dynamically forever, what does the training data actually look like across time? Neither the engineering approach nor the architectural approach has seriously engaged with the distribution of data required to sustain a lifelong learner. This remains the unresolved third pillar of AI memory. Read in sequence. These two paths aren't competing. They are sequential chapters in the same evolutionary story. The engineering approach solves today's problem within today's constraints. The architectural approach points to how we must unify systems at the paradigm level tomorrow. But together, they point to a clear, undeniable future, a world where almost nothing about how AI systems process and consolidate information is hand-designed. To build truly autonomous agents, memory cannot just be engineered, it must all be learned.